Welcome back, everybody, as we explore the topology of the real numbers. That's just lots of fun to say. So, in our last lecture, we talked about what neighborhoods in R look like, right? So, if you're given a point X, then an epsilon neighborhood of X would be every point that lives within epsilon of X, just like a neighborhood, in a city would be a similar sort of definition. So we use those neighborhoods then to talk about what it means to be inside a set in the interior or on the edge of a set, which means in the boundary. And then at the very end of our last lecture, we had worked our way up to talking about um, open sets and closed sets. So just to remind you of the definition, if you have a set in R and its boundary is inside of the set S, then it's closed. And if its boundary is in the complement, then it's open. Um, these are not, um, if and only if conditions, though, right? It is possible that you have a set which is not open or closed because you might have one boundary point that's in the set and a different boundary point which is not. Like, for example, if you had parentheses 2, comma 5 bracket, right? So the 5 is a boundary point which is inside the set, but the 2 with the parentheses next to it is a boundary point which is not in the set. Right? So open sets and closed sets are going to be extremely important for all the things we're going to be working on throughout the rest of this class because we're going to be super excited to learn about how points get close to one another and what that really means because that's going to give us limits. And we're building up all the machinery to really truly understand calculus. And of course, limits are the central idea of all of calculus. So you may notice if you Google around on the web or you look in other places that there'll be definitions of open and closed sets that don't look like ours. Right? I like this definitions because it's pretty easy to understand, and we only need to know what boundary points are, which were pretty easy to understand the definition of open and closed. But there are lots and lots and lots of other definitions for open and closed. For example, a set is open if and only if every point in S is an interior point. So another way of saying that is a set's open if it is equal to its own interior. Okay? Um, that is often taken as a definition instead of our definition. And so if you Google or look in other books, you may see this as the definition. Um, let's prove this though and show that our definition, is the same as every point being an interior point. Well, okay, so first off, since we spent a very long time building up the machinery to write proofs, let's notice that this theorem we're about to try to prove is an if and only if statement. Notice the IFF, which means it's an implication that goes in both directions. So we're going to have to prove, that being open implies every point is an interior point, and then we got to go it the other way around. We've got to assume that every point is an interior point and show that the set is open. In other words, I'm going to do a direct proof and I'm going to do it in both directions, direct proof both ways. It's really, really helpful now that we're going to start doing more sophisticated and longer sorts of proofs to stop when you see a proof in the book or in the lectures to stop and ask yourself, what kind of proof is this? Is this a proof by contradiction? Is this an indirect proof? Is this a direct proof? Maybe they did a direct proof in one direction and an indirect proof to do the other direction if it's one like this where you have to prove two ways. Um, writing out what that means, what the structure of the proof is, goes a long way in helping you understand what's going on. And that's why we did all of that in understanding all the different kinds of proof techniques. So this one's pretty straightforward. We're going to do a direct proof, which means that I'm going to suppose, one side of the if and only if and do a lot of work to try to get to the other side. So let's suppose that S is open. That's the first part. And then I need to do a bunch of stuff to prove that every point in S is in the interior. Okay? Well, first thing to notice is the definition of open, because when you do a direct proof, right, definitions are are our best friend, right? Because we start out, we just write down on our paper, suppose that S is open. Now what? Right? Well, the only thing that we know to this point about open sets is the definition. Once we're done with this theorem, we'll know something else. We'll know that every point of S is an interior point, but we don't know that yet. So once we start out by saying suppose S is open and we're doing a direct proof, we need to start writing down, what it is we know about that. And so far, all we can say is our definition, which was that the boundary of S isn't in S, it's contained in the complement. Okay? So that's our definition. The boundary of S lies in the complement of S. Okay? All right, well, what can we do with that, right? The boundary of S is in the complement, and we want to show that every point is an interior point. Well, so how does that work? Right? Well, if all the boundary points are in the complement, then there aren't any points in S that are boundary points, right? Every point in S is not a boundary point, right? Because all the boundaries of the complement. So what that means is, you know, well, we can use the fact that every point has to be either a boundary point or an interior point. Remember, that's there is a dichotomy there, right? If you're a point in S, you're either in the interior or you're on the boundary. That's the only way it works. So if every point that's in the boundary, right, is outside the set, then all the points that are inside the set have to all be interior points, because if one of them was a boundary point, they wouldn't be in the set. So there we go. Every point in S is either a boundary point or an interior point. All the boundary points are in the complement. None of them can be interior point. None of them can be boundary points if they live inside S. So every point in S is an interior point. That's it. We just started with the definition of open and wrote down what that meant and worked our way through. Now let's go the other direction. So now we're going to suppose that every point in S is an interior point, and we have to show that S is open using our definition. That is, that the boundary is contained in the complement. Well, this one's actually easier this direction, because if every point in S is an interior point, then all the boundary points aren't in S, right? Because if every point's either an interior point or a boundary point, and everything in S is an interior point, then all those boundary points can't be in S. They got to be somewhere else. They got to be in the complement, which means that S has to be open. That was our original definition of openness. Now, this is the proof of a theorem. And this is really cool because now, if we start to do a direct proof, and we start out by assuming that S is an open set, now we know two things about S. We know our definition that the boundary is contained in the complement. We also know this theorem, which says that if S is open, every point in S is an interior point. Now we know two things, and we can start to use whichever one of those seems like it would help to prove whatever we're trying to prove. So that's very cool. Another theorem, right? We need another theorem that will also be very useful. A set's closed if and only if its complement is open. And we're going to do this one the same way. We're going to do a direct proof in each direction. Okay. And this is also often taken as the definition instead of what we did in other books. And so if you look in other books, the complement being open very well may be the definition of closed for them, and then they prove a theorem that says that a set's closed if it contains its boundary, okay, which was of course our definition. Okay, so before I start assuming one side and proving the other, let me make a brief comment first. It's sort of obvious, but I'm going to use it in both directions. So I want to say it here at the beginning, which is the boundary of S and the boundary of the complement of S are exactly the same thing. Because remember, what did it mean to be a boundary point of S? It means that whenever you take a little neighborhood, then that neighborhood intersects S and its complement. So of course, if you're a boundary point of S, you're also going to be a boundary point of the complement, because the complement of the complement is the original set. And so it's just very easy to see, right? Okay, so I'm going to leave that up on the screen because we'll use that in both directions of what I'm about to prove. So we're going to start off in our direct proof by assuming, right, the P and then prove the Q, the way we used to do all this when we were talking about logic. So I'm going to start off by assuming that S is closed. Okay, and then what I have to do is work my way down to prove that the complement is open. Okay? And again, what does it mean to show that the complement is open? How am I going to show that a set's open? I could either show it's open with the definition, which is that the boundary is contained in the complement, or I could show that every point was an interior point because that was what our last theorem just said. Doing our definition is going to be easier here. Um, so let me show you what I mean. What would the boundary of the complement look like? Right? The boundary of R throw away S. Well, that's the same as the boundary of S, of course. We just talked about that. Now S is closed. So that means the boundary of S is inside of S. That's the definition of S being closed. Right? And of course, S is the complement of S. Right? So this says that the boundary of the complement of S is contained in its complement. That makes sense. Lots of complements running around. But what we've just shown is that the complement, R throw away S, is open because the boundary is in the complement of R throw away S, namely S itself. All right, so if that's a little confusing, you have to stop and chase through all those complements for a second and pause the video if you need to and rewind that. But it's not terribly difficult, right? In that we started out with what we were assuming that S was closed. Knowing that S was closed told us that the boundary of S was contained in S. But the boundary of S is the same as the boundary of the complement of S. And S is the complement of the complement. And when you write all that down, then it just falls out. We've shown that the boundary of R throw away S is contained in the complement of R throw away S. There we go. That says that R throw away S has to be open. Okay, let's go the other direction. Okay? Let's assume that R throw away S is open. The complement is open, and we have to show that S is closed, which means that the boundary of S is contained in S. Well, again, the boundary of S is the same as the boundary of the complement, right? And because R throw away S is open, which is what we're assuming, then the boundary of R throw away S is contained in the complement of R throw away S. In other words, R throw away, parentheses R throw away S, and that's just S. So there we go again. Right? The boundary of S is contained in S, so S has to be closed. Okay? All right, so this may be a little confusing when you first see this because we did it all in one step. Right? I could have broken this down into several steps where I didn't write it all on one line, but then that would be hard to see on one slide. So if you're doing this, in your own homework and you want to say, instead of all one line, the boundary of S is equal to the boundary of the complement of S, but that's contained in the complement of the complement of S because the complement of S was open, right? You could write that in several sentences. Again, make sure you understand how this works because this is exactly the kind of proofs we'll see in the homework and of course we'll see on exams. Okay, so to see if you're following along here, here's a quick quiz that you can quiz yourself. Now, obviously, this is not for a grade or anything, but stop for a second and see if you can figure out, okay, pause the video here, see if you can figure out whether R is open or whether the empty set's closed. Those are two great questions. And if you can see how that works, then you're following the definition along reasonably well, I think. So right, pause it for a second, pull out a scratch sheet of paper and see if you can prove or disprove, right, whether R is open or whether the empty set's closed. Okay, everybody back? All right. So the answer is to both of these questions is yes. Right? And so let's see why this has to be true. So R has to be open, and its complement then has to be closed. Why is R open? Well, every point of R is an interior point. Why is that? Because if you take a point in R, let's call it X, then you take a neighborhood of radius, pick any number you want to, like 1 or 7 or 10 billion, and let that be your epsilon, and then look at that epsilon neighborhood around X. Well, that's an interval that's full of real numbers. It'll still be contained in R, right? It doesn't you don't run off the end of R, right? So whatever epsilon you pick, whatever neighborhood you have around X, that neighborhood is still full of real numbers. So that neighborhood will be contained in R, which means that X is an interior point. And we had the theorem a few minutes ago that said if every point is an interior point, then your set is open. Notice that I picked a point like x, it was an arbitrary point, so that I could prove that every point was an interior point. Right? I left it as a variable. We spent a long time on proofs, right? So we would be able to use it when we got to this point. So everybody believes that R is open, right? Because every point has a neighborhood around it that is completely contained inside of R. Of course, the complement of R would be the empty set. R throw away R would be the empty set. And so if R is open, then the complement has to be closed. That was our last theorem. Right? Another way of saying this is, of course, R has to contain its boundary. Right? There's really no boundary, right? So R is also closed. The empty set is also open. Right? This is really weird because the empty set and R are both open and closed at the same time. Right? There is no boundary for R, right? So the boundary of R is the empty set, and the empty set is contained in R. Therefore, R contains its boundary. This is really kind of weird. And in fact, R and the empty set are the only sets that do this normally. So if you had a set that was disconnected in several pieces, then that might not be true. But if we're just talking about all of R, then this kind of thing is what happens when you have a set that comes in one piece. The only time it can be open and closed is if it's all of R or the empty set. This also lends itself to a great excuse to do a proof that's vacuous. Let me tell you what I mean. Let's try to prove that the empty set is open just using the definition and going through it step by step. So what does it mean to say that S is open? Right? A set S is open if for every x inside of that set S, again, means that every point's an interior point. What does it mean that every point's an interior point? For every point that's inside of S, there is an epsilon greater than 0, right? So that the neighborhood around x of radius epsilon is contained in S. In other words, this says for every x is an interior point. That's essentially what that says, right? The last half of that is the definition of being an interior point. And we know that S is open if and only if every point inside of S is an interior point. That was the theorem we did, a couple screens ago. Well, let's rewrite that a little bit because that's logically equivalent to an implication. So instead of saying for every x, blah, 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 I could say this. If x is contained in S, that implies that there is an epsilon so that the epsilon neighborhood around x is contained in S. Everybody see how that's exactly the same thing? I've turned that quantifier statement into an implication. Of course, it means exactly the same thing. Now this is where the coolness happens because now I have an implication I'm trying to prove that x contained in S implies all the rest of that. So how do I prove a P implies Q and so forth? Well, let's do a direct proof. So let's assume that X is contained in this. We're trying to prove the empty set is open. So instead of S here, I'll have the empty set. So let's assume that X is contained in the empty set. Wait a minute, there's a problem, right? That's weird, right? Well, X contained in the empty set is a false statement because X is not contained in the empty set. And you remember back when we talked about um, implications that P implies Q, right, would be a true statement whenever the P was false. Right? So sometimes we would say things like false implies whatever. That's a true statement. Right? So the statement that if X is contained in the empty set, which of course it isn't, so that's false. If X is contained in the empty set, that implies there exists an epsilon, so that the epsilon neighborhood of X is contained in S. That's vacuously true because the entire second half, the Q half, doesn't matter what that is. As soon as the first part is if X is contained in the empty set, then the second part doesn't matter. The whole statement will automatically be vacuously true. That's really cool, and this is one reason why we did spend some time on, that oddness that seemed at the time about P implies Q, and that implication will be true if the P is false. Okay, so let's sort of collect a few more things about open sets and closed sets before we move on to the next big idea about the topology of R. So if you have two or more open sets and you union them together, then that union will still be open, right? So suppose you have two open sets and you throw them together, they'll still be open. This is not difficult to prove because what does it mean for sets to be open? It means that every point's an interior point. That's one way to say it. And so an interior point means there's a little neighborhood around me, which is also in the set. Well, suppose they have a bunch of open sets, and every point inside each of those individual open sets has a little neighborhood around it, which is contained in its original open set. Then, of course, when you union them together, that neighborhood will be contained in the union. So there we go. You can union up, you know, two sets together that are open, and the result will still be open. You could union infinitely many open sets together, and they'll still be open. You could union uncountably many open sets together, and the result will still be open. So I think, oh, that's really cool. What about closed sets? Closed sets don't quite work that way, and intersections don't quite work that way. So if you intersect finitely many open sets, the result will still be open. Okay? Because the problem with intersections is if you have a point and he has a little epsilon neighborhood around him, right? And then you start taking intersections. Well, the point may stay in the intersection, but those neighborhoods might not. And so if you get infinitely many of them, you may whittle away the neighborhood down to nothingness. But if you just have finitely many of them, then you can whittle the neighborhood down, say 7 or 8 times or 200 times, a finite number of them. There'll still be some neighborhood left. So when you union up ever how many open sets you want to, you union them together, the result will be open. If you intersect them too, you can only guarantee that the result will be open if you intersect finitely many of them. And of course, closed sets is exactly the opposite. If you intersect any number of closed sets, uncountably many closed sets, you intersect them all, the result will still be closed. But if you start unioning closed sets together, then you can only guarantee that the result's going to be closed if you do finitely many of them.